Hi everybody, I'm going to teach you about force diagrams. This tutorial and the practice that follows is probably the most important aspect of this entire chapter. This is going to set the groundwork for all future problems where you're going to apply what you learn here to solve problems. The main lesson here are force diagrams. That's going to come later in the tutorial, maybe even a second one if this runs long. This is all about applying the second law of motion, which you learned in the previous lesson. Essentially, how to predict the rate at which something is going to change its motion based on the amount of forces acting on something. We have to take into account how much force and in what direction the force is. In order to do that properly, you got to draw diagrams identifying all possible forces. That's really what this is all about. We don't want to take shortcuts. In the previous lesson practice, you had some experience with force diagrams where I had an object and arrows were pointing certain ways and you add or subtract the forces. So that's what we're going to do, but we have to be able to identify forces conceptually and then go from there. So this is not going to be so much numerical as it is going to be general ideas. So pay close attention, come into class with questions. I'm going to ask you to do some of this on your own, and then we will reinforce it, and hopefully you'll have a good start. So let's start off with a problem. So let's going to center on our fat cat, El Gato Gordo here. Okay, so you're told that the cat has a mass of 6.6 kilograms, and it's lifted up with a force of 70 newtons. So we learned that the unit of force is a newton, which is equivalent to a kilogram meter per second. So according to the second law of motion, what must be the cat's acceleration? And so I'd like you to show your work here. Okay, so pause right now and do that, please. So here's what I'm anticipating many of you did. I could be wrong. I apologize if I am. You said, okay, A is F net over M. That's the second law. You put in 70 newtons for the force. You'd put in 6.6 kilograms for the mass and got 10.6 for the acceleration. And that makes perfect sense. You did almost everything right, but, okay, this is not right. The answer should be 0.8 meters per second squared. Right? In other words, a cat's barely going to accelerate upward. So maybe you kind of anticipated why that is, but you didn't know how to deal with it mathematically. So let me show you what you should do here. You don't have to change all your work, but I want you to understand that this is where the power of force diagrams come in. Okay, so the lesson for the second law, to correctly apply, you must establish all the forces acting on the body or the system. Okay, so our body here is the cat. So you know there's 70 newtons up, so I'm going to let that represent an arrow. So I'm going to put an arrow on a cat pointing up, and I'm going to label that 70 newtons. So I asked myself, are there any other forces acting on a cat? And yes, there is. There's gravity. So I'm going to draw, and we know gravity acts down, and you don't know this yet, but the force of gravity on a cat is around 66 newtons. Not quite that. If I want to be more exact, it's actually closer to 65, so I'll try to be more exact. So now I can say F net. So what I say is A is still F net over M. That's always true. But my F net is going to be 70 minus 65, and then I divide that by the 6.6 kilograms, newtons, and that's where I get around 0.8 newtons per kilogram, and I believe we discussed before that's the same as a meter per second squared. Okay, so we want to do this properly, and that's what I'm going to emphasize. We don't want to take shortcuts. Let's not do that early on. It requires a proper force diagram. And I'm going to label that, abbreviate that as FBD. Okay, free body diagram. So when you see that, that just means a force diagram. So in order to do a force diagram, to do something like we see here, we have to understand what forces are you expected to be aware of in common situations. So here's the next part. Basic forces. This is something I expect you to refer to the first few days after we start practicing, because you're not going to have this down in memory, but you will eventually. So there's not a lot of forces. We got 5 general forces for you to consider. So that's not asking too much. The first one covers almost all forces, and that's a generic applied force. A contact force. That's a push, a pull. Okay, normally I might label that, I'm going to put in parentheses here what we've symbolized. So it's a force with an F, and I'm going to use an A. So we're going to use a lot of subscripts now, A for applied force. Okay, and it's a contact force. There's some object external to the cat, let's say, that's pushing on it, pulling on it, throwing it, tugging it, whatever verb you can come up with. But it's important that it is external to the system. The system is what we're interested in figuring out what happens to it. So again, in this case, the cat is our system. It's just one object. So in the previous problem, it was whatever was pulling up on it was an external force. And now it's not always obvious whether there is an external force acting on something. So one thing that helps make it clear, and this is super important, we're going to really try to emphasize this, is there must be an identifiable object exerting that force. If you can't name what is literally pushing on the cat or pulling on the cat, then it doesn't exist. And we don't want to use the idea of momentum or impetus. We already learned that doesn't keep something moving or not. So don't put something there just because something is moving. There's got to be something pushing it. All right, next one is we're familiar with is gravity. We're going to investigate gravity in much greater detail a little later on. But for right now, here's what I want you to know. We symbolize it F sub g. Okay, force of gravity, not little g. Little g is acceleration due to gravity. And what we should know right now is that it always acts downward. And downward really means towards the center of the earth or towards the ground. Okay? And then so I said before, there's got to be an object that exerts the force. So what object pulls on the cat or pulls on us via the force of gravity? So gravity is not an object. It's a force that some object exerts on us. And that's the earth. If you go to the moon, then the moon exerts the gravity. And like I said, we'll investigate that in more detail. But right now, understanding the earth is exerting this force. Okay, next one is a general class of force that is everywhere in our lives. We often ignore it. In many problems, we pretend it's not there, but we want to be aware of it. So the general category of these are resistive forces. Okay, and I'll give a symbol for each one. Resistive forces always oppose what you're trying to do. Okay, so two classic examples. Friction is one. So friction, we designate with an F sub F, force of friction. And what friction occurs when you're trying to slide across a surface. So two surfaces are rubbing against each other, there's going to be friction. So the object that generally applies friction to a cat, if we're trying to drag the cat across the ground, or a car, is the ground itself. It could be a road, it could be the floor, some aspect of that. The other one that's all very important is air resistance. We've talked about that with free fall and projectile motion before. Okay, I don't have a special symbol for air resistance. Maybe I'll call it FD for drag, but you can use whatever you want. Don't use FA because we like to use that for applied force. All right, this is when you move through a fluid. Okay, that fluid could be air, which is most often the case. It could also be through water. When you try to run through water, you get quite a bit of resistance of the water pushing back on you. Okay, so the object, let's just say usually is air, but it doesn't have to be. Next one is imagine we attach a rope or a chain or a string to something and we pull the string which is attached to something else. And so you understand that that string becomes taut. It's not slack. It's not drooping usually. So what we can measure about that is something called tension. Okay, and tension we'll call F of T, and that's the force transmitted through a string, rope, etc. Okay, so the actual object, so if I attach a leash to a dog and we're, pulling the dog or letting the dog pull us, it is the actual rope or the string that's doing the object that's pulling on us. So we're using that rope as like a intermediary between me and the actual object I want to push or pull. Okay, what we want to know about tension, and we'll investigate this more in detail later on, is it always acts along the string, the rope, etc. So if I have a rope that is like this, then the tension might be a vector that's pulling along there. We'll investigate that more, but I just want to introduce that now. Okay, so I don't know what just happened here. The last one is a very common one, and then the one you're least familiar with. So imagine me right now standing in front of the smart board. Okay, I'm standing on the floor, or you're sitting down or lying down somewhere as you watch this. So I'll go back to me. We know that the force of gravity is acting on me, yet I'm not in free fall. So we can deduce that if my motion is not, if I'm not moving, that there's balanced force acting on me. In other words, the downward force of gravity is balanced by an upward force from the floor. Or if you're lying in your bed, the bed itself, the mattress. Or if you're sitting in a seat, the chair. So anytime you have some object supporting your weight, the force of gravity, that object is pushing up on you. And it's pushing up on you in a direction that's perpendicular to the surface. So I'm telling you all this because that lends to the name normal force. Now, normal you think of as typical, okay, the common. But normal in math means perpendicular. So the normal force is a very important force. We call it F of n. And it's not natural force. I know I introduced the idea of natural force with Aristotle, but that was just a history lesson. That natural forces don't exist. It's normal force. And it's the force of a surface supporting an object that is pushing on it. Usually you push on an object because of gravity. Other times you can push on it. Imagine bending your knees and pushing down with your muscles and your legs. You push down on the object, it will support you. Push up on it. So normally the object is the surface, depending on what you're standing on. Floor is the most common. Okay? And again, it's called normal because it always acts perpendicular to the surface. So in other words, if I have a flat surface and there's some object sitting on it, the normal force is going to push up. If I have an inclined surface and some object is sitting on it, then the normal force is pushing up perpendicular to the surface. And so we're going to investigate all that in greater detail as we advance in this chapter. So I have 3 minutes left. I've gone through all the forces that you have to consider when you're doing a force diagram. And I'll do an example 1 or 2 in a minute or so. It's not a lot. Gravity is the main one. Applied force is anything that's not mentioned here. Friction is very common. Sometimes we'll say there's no friction. Other times we'll assume there is. And normal force is another common one. Tension we'll see here and there at the beginning, more later on. So if you want to be successful from here on, besides understanding the forces, you want to follow this recipe for success. This is how you go about drawing force diagrams and then using the force diagram to find the net force acting on something and using the net force in the second law of motion to find how the object changed, namely the acceleration. I will let you read through this. Please do so. Come up with any questions, but it's best right now. Let's put it into practice. Okay, so I'm going to do 1 or 2 of these. You're going to then try the rest, and then we'll go over it in class. So here are the directions up here. So I'm going to go through one at a time. So for each situation, read the information, determine the following. Whether the forces are balanced or unbalanced, draw arrows representing all the forces acting on the body using the list from the previous page. Name the forces and identify the object exerting the force. Use arrows that indicate relative magnitude and direction. In other words, if something's bigger than another, make the arrow longer. And then if the forces are the same, use the congruent marks. And then express F net. So we're trying to do this recipe for success. So let's start with the first situation, a simple one. We drop a cat on the moon. So I chose the moon because the moon doesn't have an atmosphere. Okay, so there's a cat, it's falling, here's the surface of the moon, so to fill out that. So what I have up there, A, B, and C, doesn't have to be done in any particular order. It depends on how you approach it. So let's see if we can identify the forces. First one, is there an applied force? Is there something external to the cat, other than the ones that we mentioned after that, that are acting on it? The answer is no, there's nothing pushing on a cat. Next one, is there gravity? Yes, gravity's on the moon. We know gravity's down, so I'm going to put a downward arrow. I'm going to call it F sub G. I'm going to put in parentheses, what's the object exerting that? The moon. The moon is exerting a force on a cat. The cat cannot exert a force on itself. All right, is there any resistive forces? No, there's no drag because we're on the moon. We're not sliding across the moon, so there's no friction. Is there any tension? Nope, there's no string or rope involved. Is there normal force? No, while it's falling, it's not on the surface, so the surface isn't supporting it. So we've got all our forces, and here is my diagram to reflect that. So what can I say about it? It's unbalanced because there's nothing to balance gravity, and F net is simply Fg. Okay, So I'm running out of time. I'll do more in the next video.